Hello everyone, welcome to the lecture of this course Heat Transfer. So today we will be discussing the last module of this course, that is known as the mass transfer. So earlier, while discussing the heat transfer, we have seen that it is the transfer of heat due to the temperature difference. Now today we will study the mass transfer concept. So similar to this heat transfer, this mass transfer, it is the transfer of mass due to the concentration difference of the species in a mixture or in case of a system. So while discussing the heat transfer, we have seen that there are different modes of heat transfer like conduction, convection and radiation. So similarly, in case of mass transfer also, we will study that there are three different modes of mass transfer, and those are the diffusion, then convection and by change of phase. So all these different modes of mass transfer and their related formula we will study in details in this lecture. Okay, so let us start this lecture. So this mass transfer, it may occur in a gas mixture or a liquid solution or a solid. So this mass transfer, it occurs whenever there is a concentration gradient of a species. So what is this actually? This concept of the mass transfer. So in case of a system which consists of one or more components where the concentrations are varying from point to point. In that case, there is actually natural tendency of the transport of different species from the region of high to the low concentration. So this is actually similar to the heat transfer concept. So this process of transfer of mass as a result of species concentration difference in a system or mixture, this is actually called the mass transfer. So let me discuss again this concept of the mass transfer, that if in a system which consists of one or more different components whose concentrations are varying from point to point, in that case there will exist a natural tendency for the transport of different species from the high concentration to the low concentration. Now this process of transfer of mass as a result of the concentration difference of the species in a system or the mixture, this is known as the mass transfer. Now as long as there will be the concentration difference of the species in the system or the mixture, the mass transfer will occur in that system. So the basic mechanisms are the same whether the phase is a gas, liquid or a solid. Now there are different examples of this mass transfer like humidification of air in cooling tower, then evaporation of petrol in the carburetor of an IC engine. Next, like dissolution of sugar added to a cup of coffee, that is happening in our day-to-day life. Then the transfer of water vapor into dry air, drying or evaporation. So all these things are the examples of mass transfer. Now, as I said earlier, that similar to the different modes of heat transfer which we have studied earlier, that conduction, convection and radiation, there are also three different modes of mass transfer. So what are those three different modes? So those modes are actually mass transfer by diffusion, then the mass transfer by convection and the mass transfer by change of phase. Now this mechanism of mass transfer, it actually depends on the dynamics of the system in which it occurs. So the first mode of mass transfer, this is actually by diffusion. It is also written as molecular or eddy diffusion. So what is this actually? So this, the transport of water on a microscopic level as a result of diffusion from a region of high concentration to a region of low concentration in case of a system or mixture. If it happens of liquid or gases, it is called as molecular diffusion. So what is that? In case of a mass transfer, we know that due to the concentration difference from high concentration to low concentration in case of a system or mixture, the mass transfer happens. So what will happen in case of mass transfer by diffusion mode? So the transport of water on a microscopic level as a result of diffusion from a region of high concentration to a region of low concentration in case of a system or mixture, it is called as molecular diffusion. So it happens in case of a liquid or gases. Now this mass transfer by diffusion, it occurs when a substance diffuses through a layer of stagnant fluid and may be due to concentration, temperature or pressure gradient. Now in a gaseous mixture, the molecular diffusion, it occurs due to random motion of the molecules of the gases. So this is the concept of the mass transfer by diffusion. Now again within bracket we can see that it is written as eddy diffusion. Now when one of the diffusing fluids is in turbulent motion, then the eddy diffusion takes place. So this is the eddy part. That eddy diffusion, it is written, it is the highly turbulent water mass. So that's why this it is written when that eddy diffusion. That means when one of the diffusing fluids is in turbulent motion, then the eddy diffusion takes place. Now this mass transfer by eddy diffusion, it is more rapid than by molecular diffusion. So what may be some example like this eddy diffusion, like the dissipation of smoke from a smokestack. So the turbulent motion, it causes the mixing and transfer of the smoke into the ambient air. So such type of eddy diffusion, these are much more rapid compared to the molecular diffusion. So this is the concept of the mass transfer by diffusion. Next mode of mass transfer, it is by convection. The convection mode of heat transfer we have already discussed. Now this convection of mode of mass transfer. So what is that? This mass transfer by convection, it involves transfer between a moving fluid and a surface, or it may happen between two relatively immiscible moving fluids. Now this convective mass transfer, it depends on the transport properties and on the dynamic characteristics of the flowing fluid. So what is this dynamic characteristic? Dynamic characteristics means the flowing fluid, if it is laminar or turbulent. So this convective mass transfer, it also depends on the nature, that is the laminar or turbulent properties of the flowing fluid. Like the evaporation of ether, this is one of the example of mass transfer by convection. So next we are having the mass transfer by change of phase. So the change of phase concept, it is very much familiar to us. So this mass transfer occurs whenever a change from one phase to another takes place. So this is the change of phase. Now this mass transfer in such a case, that is in case of this change of phase, it occurs due to simultaneous action of convection and diffusion. Okay, so in case of this change of phase mass transfer, the simultaneous action of convection and diffusion, these are needed. So suppose some hot gases, these are escaping from the chimney. So there it happens due to the convection, and then it gets diffused into the air above the chimney. So this is the change of phase mass transfer. So where first the hot gases are escaping from the chimney by convection, and after that those hot gases, these are getting diffused into the air above the chimney. So these were the concepts and examples of the three different modes of mass transfer, which are by diffusion, convection, and change of phase. Now, so let us discuss this diffusion phenomena. So here you can see that Fick's law it is written. So as in case of the conduction mode of heat transfer, we have seen one rate equation that is known as the Fourier's law of heat conduction, which we have seen earlier, and from that Fourier's law of heat conduction we have got the concept of thermal conductivity. So similar to that Fourier's law of heat conduction, we are having one Fick's law in case of this mass transfer. So the linear relation between the rate of diffusion of chemical species and the concentration gradient of the species. So now this Fick's law, it will be discussed in the next slide and the next lecture in details. Now there is another terminology that is thermal diffusion. So in this thermal diffusion, the diffusion due to a temperature difference. So in case of the concept of the diffusion mass transfer, we have seen that it may happen due to the concentration, temperature or pressure gradient. So when there is the temperature gradient exists, in that case it is known as the thermal diffusion. So usually negligible unless the temperature gradient is very large. Next we are having the pressure diffusion. So in that case the diffusion due to a pressure gradient happens. It is also usually negligible unless the pressure gradient it is very large. Next we are having the forced diffusion. So in this forced diffusion, the diffusion due to external force field acting on a molecule it takes place. The forced diffusion occurs when an electrical field is imposed on an electrolyte, like in charging an automobile battery. So this is the example of the forced diffusion. And lastly, we are having the Knudsen diffusion. So what is this? The diffusion phenomena occur in case of the porous solid. So this is the example of the Knudsen diffusion. Now, whenever there is concentration difference in a medium, nature tends to equalize things by forcing a flow from the high to the low concentration region. So in this diagram, we can see that water and salt is getting mixed here. So after some time, after the proper mixing, due to the tendency of nature, which tends to equalize the things, so there will be a mixture of salty water. That means the transfer of mass from high concentration to low concentration it is happening. Now the molecular transport process of mass it is characterized by the general equation. The rate of transfer process, this is the driving force divided by resistance. So different examples we have discussed in case of the mass transfer. So one more example here, that let us consider a tank that is divided into two equal parts by a partition. Now initially the left half of the tank it contains nitrogen gas while the right half contains the oxygen at the same temperature and pressure. Now when the partition is removed, the nitrogen molecules will start diffusing into the air while the oxygen molecules will diffuse into the nitrogen. Now if we wait long enough, then we will have a homogeneous mixture of nitrogen and oxygen in the tank. So such kind of example of mass transfer process we have already seen earlier. A liquid in open pail of water evaporates into air because of the difference in concentration of water vapor at the water surface and the surrounding air. So these are different examples of the mass transfer. Like a drop of blue liquid dye is added to a cup of water. Then the dye molecules will diffuse slowly by molecular diffusion to all parts of the water. Similarly, here also the mass transfer due to the species concentration difference from high concentration to low concentration it occurs. So now let us discuss these concentrations. So now the mass concentration or mass density. The mass concentration or mass density, if we denote by rho A for the species A in a multi-component mixture. So this mass concentration, it is defined as the mass of this species A per unit volume of the mixture. And the unit is kg per meter cube. Next, the molar concentration or the molar density. The molar concentration, the notation is Ca of the species A. It is defined as the number of moles of species A per unit volume of the mixture. The unit is kg mole per meter cube. Now the mass concentration and molar concentration, they are actually related. The mathematical representation of the relation, it is Ca equals to rho A by Ma. That is the that is the molar concentration. This is the ratio of mass concentration and the molecular weight of the same species. Ca equals to rho A by Ma. Now next the mass fraction. Now this mass fraction, that is m star A, it is defined as the ratio of mass concentration of species A to the total mass density rho. So that means m star A, this is rho A by rho. And the mole fraction, though in this similar manner, the mole fraction acts in terms of total mole concentration of the mixture. See, it is defined as x equals to Ca by C. Now in a binary mixture of A and B, the following summation rules are applicable. That is rho A plus rho B, this is equals to rho. Then Ca plus Cb, this is equals to capital C. Then m star A plus m star B, this is 1. And xa plus xb, this is equals to 1. Now this concentration in case of a gas phase, this is actually expressed by partial pressure. So the concept of partial pressure, it is already discussed. We are familiar with this while we have studied the thermodynamics. And according to Dalton's law of partial pressure, total P equals to Pa plus Pb in a mixture. Now for the perfect gas law, we have PAV equals to NaGT. Also this molar concentration Ca equals to Na by V. This is equals to rho A by Gt. From the perfect gas law, you can write this. So that means X equals to Ca by C. So this is ultimately equals to rho Pa by P. And capital C equals to Ca plus Cb. We can see this relation in 13.5. So this is equals to rho Pa by Gt plus Pb by Gt. So this is equals to capital P by Gt. Now here G, it is the universal gas constant. So this is equals to mR, and the constant value is 8314 joule per kg mole Kelvin. So all these relations, these are very much useful while solving the numericals that will be discussed later. So till now we have discussed the concentrations. So right now we will discuss the velocity part. So the bulk velocity of a mixture in which different components may have different mobilities is computed either on mass average or molar average basis. Now in a fluid mixture of two components A and B, if UA and UB are the mean velocities of the components, then the formula for the mass average velocity U mass equals to rho A UA plus rho B UB divided by rho, or U mass equals to m star A UA plus m star B UB. In a similar manner, the molar average velocity can be written that U molar equals to x A UA plus x B UB. There are some more form equations like the mass diffusion velocity of component A equals to UA minus U mass. Then the mass diffusion velocity of component capital B equals to UB minus U mass. And in case of the molar diffusion, similar formulas are there. So all these formulas you need to remember to solve the numericals. So next we are having the fluxes. The flux of mass transfer, it is actually caused by the existence of different velocities and concentrations. Suppose for species A of multi-component mixture, absolute flux equals to rho A UA. The bulk motion flux equals to rho A U mass, and the diffusion flux, this is equals to Ma by capital A for the species. Now this quantity diffusion flux, that is ma by A, it represents the mass flow per unit area per unit time. So the absolute flux of any constituent as seen by stations observer, this is equals to diffusion flux plus bulk motion flux. Now the formula for the diffusion flux, that is ma by A, which is actually the mass flow per unit area per unit time. So this is equals to rho A multiplied by UA minus U mass. And in case of the molar concept, the diffusion flux equals to m star A UA minus U molar. So these are the different concepts and different formulas related to the concentrations, velocities and fluxes in case of this mass transfer. Now based on all these formulas, we will now discuss different numericals. So the first numerical, it says the molecular weights of the two components A and B of a gas mixture are 24 and 28 respectively. The molecular weight of gas mixture is found to be 30 if the mass concentration of the mixture is 1.2 kg per meter cube. Then determine number 1 the molar fractions, number 2 the mass fraction, and number 3 the total pressure if the temperature of the mixture is 290 Kelvin. So this is the problem given here, and we need to find three different things, which are molar fraction, mass fraction and total pressure considering the temperature of the mixture is 290 Kelvin. Let us first write what are the things given in this numerical. The molecular weight of the mixture A, that is Ma, it is given 24, and the molecular weight of the mixture B, it is given, which is double the molecular weight of the mixture A, that is 48. Now the molecular weight of the gas mixture, it is given 30. So total M equals to 30. Now the mass concentration of the mixture, it is given 1.2. So that means rho equals to 1.2 kg per meter cube. And the temperature for this mixture, it is given 290 Kelvin. Now the mole concentration of the mixture, we need to calculate here. So that formula C equals to rho by M. The value of rho is given 1.2 and M is given 30. So the value of mole concentration of the mixture, we are getting 0.04. Again, this capital C, this is equals to the molar concentration of A and molar concentration of B. That is capital C equals to Ca plus Cb. This formula we have seen earlier. So this Ca plus Cb, this is equals to 0.04. Again, rho A equals to MaCa and rho B equals to MbCb. So that means rho A equals to 24 Ca and rho B equals to 48 Cb. But rho A plus rho B, this is equals to rho, which is 1.2 given. So that means 24 Ca plus 48 Cb, this is equals to 1.2. Now solving the equations 1 and 2 here, we will get the value of Ca, this is equals to 0.03 kg mole per meter cube, and the value of Cb we will get as 0.01 kg mole per meter cube. So based on this value of Ca and Cb, we can calculate the value of rho A and rho B, which we are getting as 0.72 kg per meter cube and 0.48 kg per meter cube. Now the first part of this numerical, it is to calculate the molar fraction. So the molar fractions are Xa and Xb for these two different components A and B. The formula for Xa, this is equals to Ca divided by C. So Ca, this is actually 0.03, which we have calculated, and capital C, this is 0.04. So Xa, this is equals to 0.75, which we are getting here. Next, the molar fraction of X for the species B. So this is Xb, which we are getting Cb by C, and the value we are getting here 0.25. So this is the answer the first part of this numerical, that is the calculation of the molar fractions. Next we need to calculate the mass fraction. So the formula for the mass fraction of this species A and B, these are actually m dot A, this is rho A by rho, and m dot B, this is m star B, this is equals to rho B by rho. Now these values of rho A, rho B and rho, these are known to us. Rho A and rho B we have calculated earlier, and the value of rho, this is given in the numerical. So based on those values we have calculated the mass fractions, that is m star A, this is equals to 0.6, and m star B, this is equals to 0.4. And for the last part of the numerical we need to calculate the total pressure considering the temperature at 290 Kelvin. Now using the perfect gas equation, PV equals to mRT, so that means P equals to rho RT. So again this R equals to G by M, so that means P equals to rho GT by M. Now this G equals to mR, that is 8.314 kg per kilojoule per kg mole Kelvin. Now if we put these values in the formula of this total pressure, then we are getting the values of the total pressure as 96.4 kPa considering the temperature 290 Kelvin. So this is the procedure to solve this numerical, where we have used all the formulas related to the concentrations, velocities and fluxes. Let us discuss the next numerical. So it is given a vessel contains a binary mixture of oxygen and nitrogen with partial pressures in the ratio of 0.21 and 0.79 at 15 degrees centigrade. The total pressure of the mixture is 1.1 bar. We need to calculate the molar concentration, the mass densities, mass fractions and molar fractions of each species. So these four different things we need to calculate here. So the temperature, it is given 15 degrees centigrade, so that means 288 Kelvin, and the pressure, total pressure of the mixture, it is given 1.1 bar, so it is 1.1 into 10 to the power 5 Newton per meter square. So first we need to calculate the molar concentrations of this oxygen and nitrogen. So the formula to calculate the molar concentration of the oxygen CO2, this is equals to PO2 by GT. Now this PO2, that is the partial pressure of the oxygen, it is given 0.21, and this G and T, these are also known to us. So using these values you can calculate the molar concentration of the oxygen, which we are getting 0.00965 kg mole per meter cube. Again, in case of the molar concentration of nitrogen, we can calculate Pn2 by GT. So the final value we are getting here, the molar concentration of nitrogen is 0.0363 kg mole per meter cube. Only we need to remember the formula for the molar concentration and partial pressure. Next we need to calculate the mass densities of oxygen and nitrogen. To calculate the mass densities, we can use this formula, that is rho equals to mc. So in case of oxygen, rho O2, this will be equals to MO2 into CO2. So the molecular weight of oxygen and nitrogen, these are actually known to us. It is 32 and 28 respectively. And CO2 and CN2 we have calculated for the first part of this numerical. So the mass densities for the oxygen nitrogen we are getting as 0.309 kg per meter cube, and for nitrogen it is 1.016 kg per meter cube. Next, for the third part of this numerical, we need to calculate the mass fractions. Now the overall mass density rho, this is equals to rho O2 plus rho N2. So the total rho we can calculate as 1.325 kg per meter cube. Now the mass fraction XO2, this is equals to rho O2 by rho, so that means 0.233, and the mass fraction of the nitrogen gas, this is equals to rho N2 by rho, so this is equals to 0.767. Now for the last part of the numerical, we need to calculate the molar fractions of each species. Now to calculate the molar fraction of the each species, we need to use the formula for the molar fraction. So that is m dot star O2, this is equals to CO2 by C. Now this CO2 and CN2, these are actually known to us, so that means total C, this is we are getting is 0.046 kg mole per meter cube. If we use this formula MO2, this is equals to CO2 by C, then if we put the known values, then we can calculate the molar fraction of species oxygen, this is 0.21, and the molar fraction of species N2, this is 0.79. So these are the procedure to calculate all these molar fraction, molar concentration, mass fraction, mass densities, all these things for such type of numerical based on the concept of the concentration, velocity and fluxes mathematical representation in case of this mass transfer. So today in this lecture we have discussed the concept of the mass transfer and how it is different from the heat transfer concept. After that we have seen different example of this mass transfer phenomena where the species concentration happens or occurs from the high concentration to the low concentration in case of a mixture or a system. After that we have discussed the three different modes of mass transfer, which are diffusion, convection and by change of phase. So then the diffusion or the eddy diffusion, it were discussed in details. After that we have discussed several mathematical representation regarding the concentration, velocities and fluxes, that is in case of the mass fraction or molar fraction or mass concentration or molar concentration. So for such various terminology we have seen the different formulas, and based on those mathematical representation or the formulas we have discussed two different numericals. Okay, so this is the end for this lecture.